Welcome, my name is Tom Irvine, and I'm the instructor for the series of shock and vibration webinar units. Again, I thank Dr. Curtis Larson and the NASA Engineering and Safety Center, NESC, for making this series of webinars possible. The topic for today is non-Gaussian random fatigue and peak response. And in past units, we've done different sorts of analyses and numerical experiments using Gaussian random time histories, but today we're going to do non-Gaussian. So we're going to perform a fatigue and peak response analysis for non-Gaussian random time history base input, and there's a parameter we're going to be talking about called kurtosis. And for a non-Gaussian random time history, the kurtosis is typically greater than 3. We're then going to take a power spectral density of our non-Gaussian random time history that we'll be generating, and we're going to take a power spectral density of that. Then we're also going to generate a Gaussian time history to satisfy that same PSD for the non-Gaussian case. And then we're going to do some analyses in terms of what's the relative damage between those two types of time history inputs. Now, broadband random stationary Gaussian time histories have kurtosis equal to 3. So anytime we've generated white noise or anytime we've generated time histories to satisfy a PSD, those have been Gaussian distributed time histories with kurtosis equal to 3. Now sometimes in contrast we generate pure sine time histories, and a pure sine time history has a kurtosis of 1.5. But anyway, the class of non-Gaussian random time histories that we're concerned with in this unit will have kurtosis greater than 3. Okay, and one of the things I really want to emphasize is I want you to develop critical thinking skills about signal analysis and the statistical parameters of fatigue damage, etc. I just want you to be smart and more capable when, for example, you're taking a time history, then taking an envelope and using that envelope for design and test purposes. So remember that phrase, develop critical thinking skills. Here are some of the statistical formulas that we're concerned with, and this slide I've actually shown to you before in the random vibration unit. So let's start off with the mean value or the average value. And for this value, we take the instantaneous time history amplitudes. You take the summation, and there's n total number of points, divide by the number of points, and then that's the mean value. And the mean value we typically represent by the Greek letter mu, at least that's what's done in many statistical textbooks. Now once we have that mean value, we can calculate what the variance is. So for the variance, we take the instantaneous amplitudes, subtract out the mean, take that difference squared, take the summation up to n number of points, then divide by the total number of points. That is the variance. And really we don't think much about variance unless maybe we're doing some kind of chi-square distributions or something or other. The more common parameter we deal with is the standard deviation. Well, the standard deviation is the square root of the variance. So that's how we calculate standard deviation. Another parameter is skewness. So if we take the instantaneous values, subtract off the mean, take that difference, cube, take the summation, divide by the total number of points n. Now here we're dividing by the 1 sigma value, that's the standard deviation value raised to the 3rd power. And this is the skewness parameter. And we're really not going to talk too much about the skewness parameter today, but it's a measure of how symmetric the histogram is about the vertical axis. Then there's kurtosis, which is very similar to skewness except for 2 differences. You take this difference, raise it to the 4th power, and the standard deviation is raised to the 4th power. And kurtosis helps us to understand the how peaked the data is, whether peak or peaked is the right term to use. Maybe I need to look that up in a dictionary, but you get the idea that the higher the kurtosis value is, the more peaks we're going to see in the data, the more prominent the peaks will be, I should say. So these are just some of the basic statistical formulas that we use for characterizing signals, more particularly random vibration signals. Okay, so let's go ahead and generate a sample non-Gaussian time history. Standard deviation will be 10, skewness will be equal to 0, kurtosis equal to 5, and 60-second duration. So let's find our MATLAB GUI for doing this. So I go to MATLAB GUI. First go to MATLAB, then type in vibration data to go to the vibration data GUI within MATLAB. That's what I should have said in the first place. Take a moment to come up. This week we're up to version 6.6 and rising. So let's go to generate signal. And we're going to go to the bottom. This is version 1.9. We calculate, and the calculation button actually opens up a new dialog. So our skewness is 0. Our duration is 60 seconds. Standard deviation is 10. We're going to do a sample rate of 20,000 samples per second. And our kurtosis value is going to be 5. And we're also going to band limit via low-pass filtering. And then we're going to save this as random underscore K5. So the K just indicates kurtosis equal to 5. Let's go ahead and calculate. Okay. A couple plots come up. Let's go back here. We're doing band limiting via low-pass filtering. And this is all preset so that the low-pass filter will be the sample rate divided by 10. Kind of put that off to, well, okay, let's complete our save. We're going to save that output array name. That's our output time history, which is the same as shown here in this time history plot. So the amplitude, it could be acceleration g or whatever amplitude that may be desired or needed. You see the 4 statistical parameters in the title. Now the skewness is close enough to 0 that we're going to say it's equal to 0. And this whole process of generating time histories for non-Gaussian distributions is a little bit tricky. So we ask for a kurtosis of 5. What we have received is kurtosis equal to 4.9. For our purposes, that's close enough, and we're just going to call this kurtosis equal to 5. Well, what happens if we zoom in a bunch of times? What do we get? What you're going to find is we do have a broadband random signal, but there are these peaks that we see more. The peaks are more prominent than would be the case for a Gaussian distribution. Now, do you remember we did the low-pass filtering at 1/10 the sample rate? That has the effect of making this more kind of a smooth curve for these different oscillation peaks there. If we had not done the bandpass filtering, this would be very jagged, where there would be wild swings between the positive and negative points. But just maybe more as a matter of style than substance, I like to do that low-pass filtering. So what we have is a band-limited random vibration time history with the statistical characteristics as shown in the title there. Okay, now this is kind of an interesting thing here. This is that histogram of our kurtosis equals to 5 time history. So we have counts versus the amplitude bins. Now, does that look like a bell curve? No, it's not a bell curve anymore. For 2 reasons, really, from the histogram. We can see that at this point here, about 0, there are a tremendous number of points there, and this is more sharper than would be the case for a bell curve. And we also have these points that go off to very low negative amplitudes and very high positive amplitudes. So we have extremes there. So we need a name for this, a qualitative name. And I've come up with a descriptive name that I've never seen in the literature, and who knows whether it'll ever be widely adapted. But as I give this presentation today, it is Halloween 2014. So just keep that in mind. It's Halloween. Come back to that in a minute. So here's how we generate the non-Gaussian time history with its statistical parameters. And I've just demonstrated that to you as I record this presentation, but I've already done a similar calculation as I was making the slide. So here's the slide version, our non-Gaussian time history, kurtosis approximately equal to 5. Now this crest factor is 7.1. That means for the slide version case, the highest point, whatever it might be, maybe it's this point or maybe one of these points down here. If we take the absolute peak value and divide by the standard deviation, that's equal to 7.1. Now for the case of broadband random white noise type vibration with a normal distribution, the crest factor, depending on duration, and can maybe be 4, 4.5 or so. That's what we've seen commonly for the work we've done in this class. But with a higher kurtosis, we also get a higher crest factor. That stands to reason. Then here's the slide version where I've zoomed in, and you can see how prominent and how sharp, relatively sharp, the peaks are compared to what would be the case if this was normally distributed. Here's the Halloween tie-in. So there's the histogram of the slide version. And I think of that as being a witch's hat. So who knows? Maybe I'll start something here and people will pick up with this descriptive label, or maybe not. Who knows? Okay, now the next thing we're going to do is we're going to take a power spectral density of our non-Gaussian time history. And probably since we have all those sharp peaks, it's best to just use a rectangular window so we don't clip the peaks, as would be the case if we used a Hanning window. I think that's better. So let's go ahead and we do choice 9. That'll give us about delta F of about 5 Hertz. Let's go ahead and take a PSD of our non-Gaussian time history. So where did we end up with? So we've already saved the time history that's non-Gaussian. So you can see that's in the workspace now. Let's go to time history, power spectral density option, power spectral density. Okay, random K5, K for kurtosis. We've run this script before on numerous occasions. This script calculates the power spectral density of a time history. The input array must have 2 columns, time in seconds and amplitude. So we have acceleration in G. We have our file name. Mean removal, yes. The mean's already 0, so it really doesn't matter which way we choose. Rectangular window, so we don't clip those peaks. Let's plot from 10 to 2000. View processing options. Choice 9. Delta F about 5 Hertz. Let's calculate that PSD. And before we even look at the plots, as important as those plots are, I want to save this, so don't forget, because we may be coming back and using this PSD in a later step. And I'm going to be extra descriptive here, and I'm going to say this is the base PSD. Okay, that's probably a different name than shown in the slides, but I want to go ahead with this one. So let's save that. Okay, now we have that PSD saved in the workspace. Park that off to the side, park that one off to the side, come back to that in a few minutes. Cumulative RMS, who knows, maybe someday we're interested in that, but not today. Okay, here's our input time history. This is the one you've seen before. It's our kurtosis equal to 5 time history. And again, if we zoom in, you can see kind of these exaggerated peaks that occur. Okay, here's what we really want to focus on. This is the power spectral density of, this is going to be a base input PSD. We're going to apply it shortly to a single degree of freedom system. So we've got G squared per Hertz, which is really GRMS squared per Hertz versus frequency in Hertz. Overall level is approximately 10 GRMS. Of course, we specified a standard deviation of 10 when we synthesized the time history. And because the mean value is essentially 0, we kind of get a little bit lazy and use the GRMS value and the standard deviation values interchangeably. So we can see this is fairly flat until we get to the roll-off portion. So this amplitude here is 0.05 g squared per hertz. This amplitude around 2000 hertz is 0.025 g squared per hertz. So it's 1/2. From here to here is 1/2. That equals a 3 dB drop. So we did a 3 dB Butterworth filter, and you can see the effect of that roll-off. Otherwise, this is flat, which is characteristic of white noise. Now, when we say white noise, I think we pretty much always assume Gaussian distribution with kurtosis equal to 3. So this non-Gaussian time history, it does have some characteristics of white noise, but given that its histogram is a witch's hat, I'm not really sure whether or not we could call it white noise. I'll have to think about that one a little bit more. Okay, so now we've got a time history and we've got a PSD. So probably you can guess what's coming next if you've been taking these webinar series for any length of time. Okay, so let's just go through the slides. So there's the slide version of the PSD for the slide version data. We already talked about the roll-off due to band limiting. So here's what really comes next. We're going to take that time history, apply it as a base input to a spring mass single degree of freedom system. This system is going to have a natural frequency of 600 hertz, a Q value of 10, and a fatigue exponent B is equal to 6.4. So let's apply that non-Gaussian time history to that spring mass system. So how do we do that? Well, we've done this before so many times. So we go to time history, single degree of freedom response to base input. Okay, our input's going to be random underscore K5, so before I do anything else, I want to type that in. So this script calculates the response of a single degree of freedom system to base excitation. The input data must have 2 columns, time in seconds, and base acceleration. So we've got English units, our natural frequency for our oscillator, 600 hertz, Q value 10. And let's go ahead and calculate the response time history. Now here's an interesting thing I want you to think about before I actually press that calculate button. Our base input has a witch's hat histogram. What kind of histogram will the response time history have? Will it also be a witch's hat? Will it be a bell curve or something in between or something different? Well, that's a little question for you, but let's go ahead and calculate, and we'll just do the experimental method, which I'm very much an experimentalist. Base input time history, this is kurtosis equal to 5 with a witch's hat histogram. You've seen that before, so I'm going to park that off to my second screen, which is out of your view. Relative displacement can be of interest if we're concerned about loss of sway space or clearance, or if we're doing a Steinberg type fatigue analysis on circuit boards. But today, just for brevity and simplicity, we're only interested in the acceleration response. So we've got our 600 hertz oscillator with Q is equal to 10. Acceleration G versus time in seconds. Zoom in a couple times. So what do you think as we zoom in a couple times? Well, what we're going to find is that the frequency content, if we take the number of positive peaks and divide by the corresponding duration, that should be pretty close to 600 hertz because our system tends to vibrate at its natural frequency. That's what it's trying to do. And most likely the response, the PSD of that response will be a narrow band random response. The amplitude is tending to vary randomly with time. Well, we're still not exactly sure what kind of histogram that is. We're getting closer, but let's actually calculate a histogram. So let I'm going to call this random K5 response. And this is a time history response. So I think I'm going to append TH here just to really make it clear in the MATLAB workspace what we're dealing with. Let's go ahead and save that. So now that response time history is in the MATLAB workspace. And we can go into our statistics function here, our dialog here. We've run this one many times before. Preloaded into MATLAB. Looks like I need to make this box a little wider. It's random underscore K5 underscore response underscore TH. Acceleration in G. Let's look at the histogram. Push calculate. Okay, so we get some descriptive statistics in the box. Still got a couple plots coming up. So we get our sample rate is 20,000 samples per second. Mean value is essentially 0. The standard deviation, 21.48 Gs. Since the mean value is approximately 0, standard deviation and RMS are equal to the second decimal place. Skewness, approximately 0. The kurtosis value is 3.1. Okay, so for a pure Gaussian process, that kurtosis should be 3.0. So it looks like just in terms of kurtosis, we're getting very, very close to being ideal Gaussian distribution, but kind of hold that thought. We're going to come back to it. You can also see the peak positive, peak negative values. Our crest factor is equal to 5. That means if we take the highest of those two values and divide by the standard deviation, that's approximately equal to 5, or you could say 5 sigma. And here again, this is one of my things I've told you several times. When you're doing random vibration response analysis, please do not assume that the peak value is 3 sigma. In this case, we have a 5 sigma response. The Rice's characteristic frequency, approximately equal to the natural frequency of 600. Okay, so this is just the statistics module. Oh, yeah, but wait, there's more. The histogram shape. So the kurtosis is almost 3, and the histogram of the instantaneous response amplitudes is approximately a bell-shaped curve. It's trying to be a bell-shaped curve, and it's very close, although not quite there yet, but very close. Now, if we take the local peak positive and peak negative values, and we take a histogram of just the local peaks, whether they be positive or negative peaks, we get a statistical distribution that is what we call a Rayleigh distribution. So we have a Rayleigh distribution of the absolute peaks for this narrowband random process. Okay, I think at this point it would be a good idea to return to the slides. Actually, we're going to do one other thing. Let's go to our rainfall fatigue. Now, we want to calculate damage, and rainfall fatigue is an intermediate step. Rainfall fatigue is not an end in itself, rather it's a means to an end. So we've run this one before already in previous webinar units. So we want to take the random underscore K5 underscore response underscore TH for time history. It's acceleration G. Just as a review, this is the rainfall cycle counting per ASTM E1049-85, 2005. The input array must have two columns, time in seconds and amplitude. Note that the amplitude in the resulting table, which you will see later, is peak minus value divided by 2. Display table, yes. Figure, yes. Actually, we're not going to really spend much time at the table at figures. We're actually just going to close those out almost as soon as they pop up. For numerical engine, I highly recommend you do what's called a MATLAB MEX numerical engine, and this is going to call up a C++ compiled program so that the MATLAB will be acting like a wrapper, and the C++ is actually going to be doing the number crunching. To do this, you need to download a C++ compiler, which you can do for free from different websites. And then there's some one-time steps. You only need to do this once so that your MATLAB can get connected up with your C++ compiler. And then there's also a source code that you have to compile for your machine. One-time steps. Okay, so we've got all of these parameters set up. So let's calculate our rainflow. Okay, I'm not really interested in the bin table. I'm not really interested in this plot. So that's a bit anticlimactic, but we just click out of those real quick. What we're interested in today is this relative damage. So this relative damage is 6.4 for our fatigue exponent. And I should have said that more properly. We're going to enter in a fatigue exponent of 6.4, which is, by the way, the value Steinberg represents for electronic equipment. Then, based on that fatigue exponent and based on these rainflow cycles, we're going to calculate the relative damage. And that's going to be equal to 9.029 e to the plus 14. So let's go ahead and I'm just going to to help us remember this number, I'm going to put it over into WordPad. So this is for kurtosis equal to 5. It's the base input is kurtosis equal to 5. So we have SDOF response 600 hertz, Q is equal to 10. Let's sort of just kind of park this off to the side. We'll come back to it in a few minutes. Okay, click out of that, click out of that. We're going to return to the slides. That's what we need to do. Okay. So there was our oscillator, and we did the response to the base input, the time domain, and we did that using the David O. Smallwood ramp invariant digital recursive filtering relationship, which is intended for shock but also works just as well for long duration vibration. Then we got our acceleration response, so this is the slide version. And we took a look at the descriptive statistics and found out that the histogram was a normal distribution approximately. And there's something called the central limit theorem. So the histogram approaches a Gaussian shape even though the input is non-Gaussian. And we're not going to go into all the statistical theory about the central limit theorem. I'll let you do that on your own. But here are just some observations from Christian Lalani or Lalane, or however he might pronounce his name. For a strongly resonant system, such as our spring mass system, subjected to broadband excitation, the central limit theorem makes it possible to establish that the response tends to be Gaussian even if the input is not. This applies when the excitation is not white noise, provided that it is broadband process covering the resonant peak. So our kurtosis equals to 5 signal was broadband. The energy went up to 2,000 hertz. Of course, there was a little bit of roll-off due to the filtering. But our 600 hertz was well within that frequency band for that kurtosis equal to 5 signal. And our signal with kurtosis equal to 5 was non-Gaussian. And whether or not it was white noise, we kind of have to be a little careful about that. But I think that, this is a wonderful statement. We might substitute non-Gaussian there for non-white. But again, perhaps when we state that a signal is white noise, we are assuming that it's Gaussian distribution with kurtosis equal to 3. So if that's the case, which it probably is, then this statement's perfectly fine as is, which is a roundabout way of saying our kurtosis equals to 5 signal is not a white noise signal. Okay, so then we did the rainflow followed by the relative damage, and we came up with something pretty similar to the values shown here for relative damage. Now imagine that that non-Gaussian time history was our actual field environment. So we went out and did a field measurement, and now we have to derive a test specification based on that field measurement. We're not actually going to derive a test specification despite what that slide says there, but we are going to derive an envelope. Now, upon that envelope, we would need to add margin, appropriate margin, to make it into a true test level. But anyways, let's just go on. So power spectral density, g squared per hertz, versus frequency in hertz. Blue curve, you've seen that before. This is the slide version for the power spectral density of our non-Gaussian time history with its roll-off. So if we were just to draw an envelope, we might draw this dark red curve here, which is 0.05 g squared per hertz from, we'll call it from 10 to 2000 hertz, and we'll be a little conservative, so we're going to have some extra margin in this roll-off region. And the fact that some blue points are higher than the other, some of the peaks are higher than the valleys, we're not going to worry about that, because if we average this all out, it would come out to be pretty much 0.05 g squared per hertz. So we're going to call this our PSD specification, and I'm going to do a little copy and paste on this for a reason that's going to become, in fact, I'm going to put down here a little bit clear later on why I'm doing this. In fact, let me just do this real quick. So we're going to have two columns of numbers. The first column, well, let's just do this little box here. It's a little easier. We've got 10 hertz, 0.05 g squared per hertz. 2000 hertz, 0.05 g squared per hertz. Now here's the situation. We could take this envelope and maybe add margin as needed, and we're going to pass that off as a design and test specification to other engineers. But here's what those design and test engineers and analysis engineers are going to assume. They're going to assume that they can meet this specification with a Gaussian distribution time history with kurtosis equal to 3. So my question to you, is that a valid approach? Is that conservative or under-conservative, or is that just about right, or what? And we're going to do some critical thinking skills and some calculations to figure that out by way of example. So the next step, we're going to synthesize a time history. It'll be 60-second long, the same as our original time history, to match that PSD. And our resulting time history will have a Gaussian distribution. So let's go to our vibration data GUI package, and we're going to input a power spectral density, and we're going to synthesize from white noise. So it's going to be 60-second long duration. The array name is going to be, okay, here's what the array name is going to be. So a few minutes ago I did that little copy and paste thing, and I need to get this all on one line. So now I have the PSD spec. You can see that in the workspace, and these are the breakpoints for the PSD. And we're going to synthesize a Gaussian time history to satisfy that PSD. Let's pick choice 9 here. Give us 512 statistical degrees of freedom. And let's go ahead and synthesize that Gaussian time history. Take a moment or so there. Get a bunch of plots, displacement time history synthesis. Just note that the mean value is 0. Velocity time history of the synthesis. Just note that that's 0. And here's the acceleration. So the acceleration and the corresponding velocity and corresponding displacements are all part of a match set. So the acceleration g versus time in seconds, GRMS values almost 10. And if we zoom in a couple of times, you can this is going to turn out to have a normal histogram. And in fact, here is the histogram. So Gaussian normal distribution, bell curve type histogram. And the kurtosis value is going to be equal to 3.0. And here's the power spectral density, g squared per hertz versus frequency in hertz. The red line is the specification. The black lines are the plus and minus 1.5 dB tolerance. The blue curve is the synthesis. That's the PSD of the time history synthesis, I should say. Well within tolerance bands. We're good to go. So let's call this the random underscore K3 because this has a kurtosis equal to 3. And I have not actually shown you that it does. I'm just saying that it does. But let's make sure that I'm being honest here. So let's go back to our statistics function, and we're going to run random underscore K3 and see what kind of okay, ignore that one, ignore that one. You've already seen that kurtosis equal to 3 time history has a bell curve there for its histogram. This gives us some additional information. We see, in fact, that the kurtosis, if we round to the first decimal place, is 3.0. So that's good. Crest factor is equal to about 5 there. Okay. So that's the statistics of this kurtosis equal to 3 Gaussian time history that satisfies the PSD, our reference PSD specification. So the next thing we're going to do is we're going to apply that to a 600 Hertz oscillator as we did before. So this is going to be kind of similar to what we did before, time history input, single degree of freedom response to base input. Our base input now is random underscore K3, 600 Hertz. And we've already run this function once today, but just as a reminder, this script calculates the response of a single degree of freedom system to base excitation. The input data must have 2 columns, time in seconds, and base acceleration. So let's go ahead and calculate. We're going to ignore the relative displacement. Here is the acceleration response at 600 Hertz. Q is equal to 10. And what we find as we zoom in is that, and we've done this sort of exercise before, this is a narrowband random response where the frequency is fairly sinusoidal at 600 Hertz. The amplitude envelope varies randomly, and the net result is a narrowband random response. So let's go ahead and save this because we might need this for another exercise. I'm going to call it random underscore K3 response underscore TH. Save that. And once we've saved that, we can go to the rainfall fatigue as we did before. So before we were doing the K5 signal, now we're doing the K3 signal. And both of these signals are the 600 Hertz response with Q is equal to 10. So is this going to have more damage than the K5 curve, about the same, or less damage? Let's see. Let's go to MEC since that's quicker. Let's calculate the pesky bin table and plot come up. Click out of both. We've got our Steinberg 6.4 fatigue exponent. Let's calculate the damage. And the damage for this case comes out to be about 1.5 e to the 15. A little bit higher than I expected, you know. So for kurtosis equal to 3.0, we've got about 1.45 e to the plus 15. So it looks like for the kurtosis equal to 3 case, it's about higher by a factor of 1.5. But you have to remember that there is, oh, okay. I was wondering why that was higher. This fatigue exponent is supposed to be 6.4. Okay. Ah, okay, that's a better number. I'm starting to sweat a little bit, saying, why did my exercise go so wrong? So for kurtosis equal to 3 with, okay, let's put the fatigue exponent B is equal to 6.4. Now these two numbers, we're really kind of fooling ourselves to go out to all these different decimal places, because these are just ballpark estimates anyways. So it looks like for the kurtosis equal to 3, we're about 8% higher. And those numbers are very similar with a slight edge going to the Gaussian kurtosis equal to 3 case. Okay, at this point, let's get caught back up with our slides. So what do we have in our slides? Let's go to full screen there. Okay, slideshow. And when I did this, I used different names, and it doesn't matter what names you use, just as long as you remember what your names are. So here's where we synthesize the time history to match that test spec, and in this case, our time history will have the Gaussian histogram distribution. So here's the slide version of that synthesized time history, which is going to be a base input. And our base input has the bell curve for the Gaussian case, obviously. Then we took a look at the 600 Hertz response. Q is equal to 10. See some descriptive statistics there. Then we did our damage calculation. Well, actually, we took a look at statistics. Okay. This just gives us some more information on the single degree of freedom response. You can see the crest factor and the kurtosis for the Gaussian case. Then here's where we did the damage for the response to the Gaussian base input, where the base input had kurtosis equal to 3. 6.4, be sure and get the right exponent there. And we got a damage value similar to what I just demonstrated. Now for the slide version, here's a comparison. So we've got our 600 Hertz system, Q is equal to 10, B is equal to 6.4. We have our non-Gaussian case where the kurtosis was 5, and our Gaussian case where the kurtosis is equal to 3. And the similarity between these two was that their respective PSDs were the same, ignoring the fact that the non-Gaussian had a little bit of roll-off towards the end. Aside from the roll-off, these two base inputs produced essentially the same PSD. So for the overall GRMS values, the non-Gaussian, these were actually the responses here. So these are the responses. The response was slightly lower for the non-Gaussian case than the Gaussian case. The peak G response was slightly higher for the non-Gaussian case than for the Gaussian. The crest factor was 5.4 and 4.8 for the Gaussian case. So, of course, since the peak value is higher for non-Gaussian, we'd also expect the crest factor to be higher as well. It's pretty intuitively clear. The kurtosis, for the Gaussian input, the response did a little bit better job of also having a Gaussian response. And for the non-Gaussian base input, the response at 600 Hertz, Q is equal to 10, had a kurtosis that was approaching the Gaussian ideal, didn't quite make it, but was very close. Now this damage metric that we looked at was G raised to the power 6.4, very similar, but we give the edge to the Gaussian input case. So again, these numbers here are for the response of the single degree of freedom oscillator, 600 Hertz, Q is equal to 10, B is equal to 6.4. And the title here, the header lines refer to the base input. So we have the non-Gaussian base input and the Gaussian base input. And again, the commonality between those two inputs is that they satisfied the same PSD, ignoring the roll-off for the non-Gaussian case. Okay, I covered those two bullets already. So it looks like that if in fact our oscillator, our component is 600 Hertz, Q is equal to 10, B is equal to 6.4, then this whole approach of doing the enveloping that we did and using the Gaussian time history base input to represent a non-Gaussian base input is okay, because these numbers are all close enough to one another. So we could substitute the Gaussian time history for the non-Gaussian environment. That would be reasonable to do. Okay, but what if one of these parameters varied? What if the natural frequency was an independent variable, or we wanted to vary Q, or we wanted to vary this B value? Would these same base input environments still produce similar results? Well, maybe not. It depends, and maybe that's something you can do for a kind of a little side experiment. So let's go ahead, and I'm going to do part of that experiment with you, then the rest you're on your own. Let's calculate something called a fatigue damage spectrum, or FDS. And this is a case where we're going to allow natural frequency to be an independent variable. We're going to fix Q equal to 10, and we're going to fix the exponent equal to 6.4. Now conceptually, the fatigue damage spectrum is similar to the SRS and the VRS functions. And the main conceptual difference is that with the FDS, we also have to note what that fatigue exponent is. So there's different ways we can do FDS calculations. We can do them in the time domain. We can do them in the frequency domain. That's one of the neat things about shock and vibration analysis. We can do it in the time domain or the frequency domain. So let's start off with a time domain calculation, and let's go to our fatigue toolbox. So we've got a time history input, and we're going to calculate the, so we're going to do a fatigue damage spectrum for an acceleration base input. So for this step here, we want our base inputs. So we're going to do this twice. So this script calculates the fatigue damage spectrum for an acceleration time history. I need to modify that to say a base input time history just to make that more clear. The input data must have two columns, time in seconds and acceleration. So we have random underscore K5. That's the first thing we did today, was we generated this non-Gaussian time history. Let's do 1/6 octave spacing. We'll start at 10, go to 2000. Our fatigue exponent is 6.4. Definitely we want to use MATLAB MEX because we're doing this calculation for a whole family of oscillators. MEX is definitely the way to go. Let's go ahead and calculate. And this is going to take a little bit of a time, so we're just going to be patient here. If this was an actual work problem, I might even go to 1/12 octave spacing, but that would take longer. But that's okay, because I'd be checking my email or taking a break. So this program is calculating the time history response of each oscillator, and then it's doing a rainfall cycle count in the time domain, and then it's doing our Miner's type relative damage calculation at each natural frequency of interest. The first plot, which is off to the right, is the traditional shock response spectrum. So we have peak acceleration G, natural frequency in hertz. Q is equal to 10. You can see the positive and negative curves there. So we got at 600 hertz, we're just a little bit above 100 G response. Let's see if we have a, okay, we got a point at 570, then the next one up is 640. So you can see somewhere around 600 hertz, the shock response spectrum is about 106 G or so, or just above 100 G. Okay, but really what we're interested in is the fatigue damage spectrum curve here. So I've got the damage index, its acceleration raised to the power of 6.4 versus natural frequency in hertz. Q is equal to 10, B is equal to 6.4. And do you remember our damage we had? It was 9.0 e to the 14th. So let's get, so if we just kind of, we don't have a point exactly at 600 hertz, and I know there's a way to interpolate plots with the cursor, but let's just if we kind of toggle back between 570 and 640, we can see that our, okay, come on, I got to push it up. We can see that this value 9.0 to e to plus 14 is right in there. Okay, so that's the case. We'll call this the FDS for the K5 input. So I'm going to save that. Now we're going to do the same thing, everything the same, except for the K3, the kurtosis equal to 3 base input. So that's the base input that has the same PSD as the K5 input. Only in this case it has kurtosis equal to 3 with a normal distribution. And I'm also going to want to save that. First we have to calculate before we can save though. So again, we're just going to have to be patient and wait. So if we're using MATLAB Direct, that might take 45 minutes. So again, I highly encourage you to use the next method. Okay, shock response spectrum. Okay, so here's the fatigue damage spectrum for Q is equal to 10, B is equal to 6.4. Natural frequency is an independent variable. The damage index with the G level raised to the power of 6.4. So at 600 hertz, we can see we've got a point at 570, one at 640. So we had a 9 point something e to the 14, so that's going to fit right in there like it should. Now let's actually save this. Okay. The next thing we're going to do is do a comparison. So let's go to our plotting utilities, and we're going to plot two curves, but even though I have a two-curve option here for plotting two curves, I prefer the multiple curve plot utility. So we've got FDS K3 and FDS K5. So K3 is the Gaussian and K5 is the non-Gaussian. The x-axis label will be natural frequency in hertz. The y-axis label will be, okay, this is actually going to be damage, and we're going to have to say G raised to, and then in curly brackets, 6.4, curly bracket, regular parentheses. Make that log as well, make this manual. 10 to 2000 hertz, plot curve 1 and 2, call it figure 7. Fatigue damage spectrum. Since there's two curves, I'll call it spectra. Note the Q value, note the B value. Plot the two curves. Uh-oh. One of those, something didn't go right. Oh, we want both axes to be log. Okay, this will look a lot better. Fatigue damage spectrum, Q is equal to 10, B is equal to 6.4. The damage is G. I meant to use an uppercase G, but I'm not going to go back and change that now. Raised to the power is 6.4, natural frequency in hertz. And the Gaussian base input and the non-Gaussian base input are very similar throughout most of the natural frequency domain. We're not going to worry about what happens at 10 hertz. Down here we kind of run into some numerical stability issues anyways. So the bottom line is that regardless of what our natural frequency is, as long as it's, say, within 20 to almost 2000 hertz, we could use this Gaussian distribution as a base input and still come up with the same damage as would be the case for the non-Gaussian, which we assume might represent a measured field environment. Now, is that a rule of thumb for all cases? Please do not assume that to be so. This is just a snapshot of one Q and one B is equal to 6.4. We have that natural frequency be an independent variable. What if we had varied Q? What if we had varied the B value? Could there be a difference? Yes, there could be. One way or the other, there could be a difference. What about if our starting non-Gaussian signal had kurtosis equal to 10. Could there be a difference even for this Q and B case? Yes, there could be a difference. Please assume that there will be a difference until proven otherwise. So there you are. There are other ways to calculate fatigue damage spectrum, particularly in the frequency domain. And let's go ahead and do that for that PSD spec we came up with. So let's go to the fatigue toolbox, and we're going to do a PSD input. Now, to calculate a fatigue damage spectrum for base input PSD, we first have to calculate the VRS. So we've run this script before. This script calculates the vibration response spectrum of a single degree of freedom system subjected to a base input PSD. And as a bonus, the fatigue damage spectrum FDS can also be calculated. The input array must have two columns, frequency in hertz, and acceleration, in our case, g squared per hertz. So we had that, was it PSD underscore spec or spec underscore PSD? Which way was it? PSD underscore spec. That was the breakpoints. So PSD underscore spec. From 10 to 2000. English units, Q is equal to 10, duration 60 seconds. Calculate both. Fatigue exponent 6.4. Acceleration, fatigue metric. Go and calculate. Frequency domain is a lot faster than time domain for these types of calculations. Okay, this is the acceleration fatigue damage curve for that specification that we came up with earlier. And just for brevity, I'm not going to actually superimpose these curves, but again, these two on the left are from time domain calculations. So we have the same damage here, same damage metric, same limits, same decades and all that. Here I used uppercase G, and here I use lowercase g, but I meant to use uppercase G. Both as a function of natural frequency in hertz over the same limits. And if you just sort of do kind of a quick eyeball, you could see if we took this blue curve and maybe turned it into, say, a green curve, and we superimposed it on these other two curves, all three curves would line up very well. You can just sort of eyeball and see that. In fact, our case of interest earlier was at 600 hertz for a specific oscillator. So if we look at, okay, in this case we do get a point around 600 hertz, and that's approximately 9 e to the 14, which is the damage number we were coming up with at 600 hertz. So it looks like when we do the frequency method, we get a little finer octave spacing by default. So anyways, these are just some tools. I hope you can use these. Let me just go back real quick and check the slides, see if there's anything I've missed before we finish off here. So we calculated the fatigue damage spectrum for the SDOF response to the non-Gaussian input. That was the time domain method of doing a fatigue damage spectrum. We did the same thing for the single degree of freedom response to the Gaussian input. And again, that was the, well, actually in the slide version here, I just went ahead and did the frequency domain method. And then I superimposed the time history FDS with the frequency FDS, comparing both the specification and the time domain method. So I did a little bit different in the slides. And those two curves line up very well. I guess probably the closing comment here. So in this example, the kurtosis difference did not really affect the damage level in terms of the relative damage, but that might not always be the case. So please be careful and use your critical thinking skills. So probably the most important thing I can say today or have said today is this last bullet on the introduction. Please, please, please develop your critical thinking skills about signal analysis, base inputs, response, the respective statistical parameters, their histograms, their relative fatigue damages, and so on. So please do these exercises as homework, and hope that you can also use these tools, these software tools, for your actual work problems. So have a good day, and we'll see you next time. Thank you.